fading light of day. It's just my ham radio where the airwaves play. There's comfort in the chatter, echoes reaching far, tales of life and laughter.
Thanks, Al. Okay, so I don't remember, a couple months ago I did a presentation on station efficiency and optimization, you know, especially for Chase and DX contesting, things like that. And it was kind of, that was maybe kind of advanced into the station management. And I thought it would be probably, we have a wide audience, wide range audience, so I wanted to back down a little bit and talk specifically about the antenna and antenna system with, you know, tuning, a little bit of tips and tricks. This is kind of going to be a hodgepodge of data and information about antennas. It's going to be mostly HF related, but there's a lot of principles that apply to VHF and UHF as well. So hopefully there's some tidbit in here that'll help somebody along the way. But before we get started too deep into this, I want to cover a couple of terms that are important when you're talking about antennas and antenna systems. First of all is DBI versus DBD. You will find not much in the, you know, you'll find some HF antennas are advertised for gain, but you're going to find huge amount of advertising on VHF and UHF antennas. I dare anybody to go to Diamond or Comet or any of those and find, and what you'll find is everybody uses DBI. And it's important to understand the difference between DBI and DBD when you're looking at, it's not just important for the gain of an antenna. It's also important to understand patterning and really how the antenna is performing. So DBI is decibels relative to an isotropic antenna. An isotropic antenna is not a dipole. An isotropic antenna does not exist. It is an antenna that radiates perfectly the same in every direction in a sphere, a ball. So, you know, that's not a real thing, right? It's also, you know, unaffected by anything around it. It's in a, you know, perfect vacuum, et cetera, or not vacuum, but, you know, no outside influences. So it's an okay number to compare things to, but it's not very realistic for us. However, it's a great number to advertise, because if you can beat an antenna that radiates like that, you know, it's going to show more gain than almost anything, you know, if you compare to isotropic. So you'll find everybody, you know, all the marketing is against DBI, not DBD. DBD is decibels relative to a dipole. So this is a perfect dipole in space. And there's a difference of 2.15 dB between a dipole and an isotropic antenna. And that is because in a dipole, you know, it's the donuts, right? The two donuts that come off of the ends. And so the energy is focused, right? The energy is not going straight up and straight down. It's, you know, it's coming out in those lobes that everybody's familiar with that look like that. So, you know, here's the major energy fields in a dipole, and there's always lobes, so you're not, you know, it's not perfect. But this is where most of the energy in a dipole is radiating. This would be your wire, you know, feed line, and your wire here and here. And this is kind of what it looks like on a polar chart as to where the energy is going. So how do you compare this to one of these model antennas? Well, this is a good way. I love this diagram. The isotropic, right? Here's your sphere. The red circle is the sphere that the energy is going everywhere. But your gain, you know, this shows the gain of an antenna. This would simply show the difference between isotropic DBI and just a standard dipole DBD. You can see already why there's 2.15 dB of difference right there, because the dipole is not radiating up and down, right? It's radiating out. So if the dipole was here, it would be through the screen this way. and the energy would be going that way, but not this way. So it's just good to know and understand the terms when you look at what you're comparing. If you're, like I said, VHF, UHF, this is big, right? They always advertise on how much gain your super gainer has and things like that. But it's good to understand what they're talking about so that you can make decent decisions about choosing the antenna, whether you're designing it or buying one. Moving on, another big one, and this is, again, all of this applies to all antennas, but you're going to find this more in the HF realm, is resistance. And ohmic loss is a term that's often used. You're not going to find these terms and things if you just go and look at the G5RV on hamradio.com. But it's really, really important because the loss, when it's typically referred to as the entire system. An antenna in and of itself is only part of the antenna system. So in ohmic loss, the sum of the resistance offered to the electron flow through the material and to the flow of ions through the electrolyte. So when you say you have loss in an antenna system, and we're going to get into what that means and where some of the energy goes and all that stuff, it's really important because you can have a phenomenal antenna with a great SWR that's terrible at radiating energy. The other thing that's really important, and this one drives me absolutely nuts in the industry, tuning versus matching. You will find every device out there to be called an antenna tuner. Occasionally, people label them as a transmatch. Well, tuning is actually is adjusting the antenna for resonant point. Matching is impedance matching between the native impedance of the transmitter or receiver and the native impedance of the antenna. Now, ideally, since we use 50 ohms for most of our transmitting antennas, occasionally 75 ohm for receive antennas in ham radio, ideally, we would use a 50 ohm transmitter, a 50 ohm coax, and a 50 ohm antenna. But that's not always the real world, right? The real world is not perfect, and it does not, it does not exist. So when we are tuning, we are adjusting the antenna for resonance, the frequency at which the antenna resonates best. When we're matching, we're impedance matching between the transmitter receiver and the antenna system. Okay, so I just talked about having a great antenna, but it doesn't radiate very well. So I want to talk about power dissipation. Once the power is generated by the transmitter and sent up the feed line, let's talk about where it can go. There are three main areas that power can go. The air, and that's where we want all of it to go, as much as we can possibly get to go. Goal is to get it and radiate it in the direction that we want it to go. The ground, this is one people don't think about much, but doesn't matter what frequency you're talking about or what kind of antenna, the ground is incredibly important because it's sometimes part of the antenna system. Sometimes it affects the rest, the antenna itself. And it's also required for things to work properly. And ground is a tricky term in and of itself, so we'll get to that. And then the third place is everywhere else. So it could be the coax. It could be back into your shack. It could be you. I know it doesn't happen much anymore in the modern age of solid state equipment, but anybody that grew up with tube radios and things will probably remember somewhere in their experimentation and career touching and feeling the tingle on the mic, or touching the chassis of the radio and feeling the tingle. That's RF coming back onto there. So, power can be transferred to less desirable places than you want it to go, and we need to be aware of that and be careful about that. So, let's talk about the first spot, and that's the air. Now, If we're DXing, we want a very low angle of radiation off of the antenna. So this diagram here shows kind of an antenna, and it shows all the different wave possibilities, right? And this is one it's really hard to see on the screen, but you'll see a little arrow here that's very close to the tower, to the antenna. That's called ground wave. So any antenna we have is going to have an area, pretty much no matter where the antenna is radiating, we're going to have a circle on the ground near the antenna where that RF is going to get to. You can be able to receive it. That's called ground wave. It's not reflected or anything else. It's just literally coming off. It comes off the lobes of the antenna. It can actually come off of radiating parts of the feed system if you're not doing it right. But that's also that's not detrimental necessarily. A ground wave can be used, for example, if we are in the bottom of the solar cycle and we want to talk to someone in 20 miles west of here, 20 miles, away from here, 10 meters, which will go nowhere in the bottom of the solar cycle typically, but it works great in ground wave. You can have a great conversation on a nice quiet section of the band in ground wave. I've had a lot of summits on the air and parks on the air contacts with people within 50 miles, 80 miles on ground wave on a dead band because of that. So now, we've got various different things, right? Which layer of the atmosphere it bounces on is going to matter. Sometimes this is called ducting when a VHF, typically a VHF signal comes up and it bounces between layers and comes out another place. NVIS, right, would be up and straight down, usually within 300 or 400 miles. And we're going to talk about that a little bit, but it's really important to understand your antenna system and where it's radiating its power. If you remember back to the last slide, I said we want to get, if the goal is to get your energy in the air, and the goal is to get it to go where we want it to go. If you're doing some DXing, you probably want a low angle of radiation, 10 to 20 degrees. If we're talking emergency communications, we want a high angle of radiation. The thing to remember about this is the antenna, although the receive and transmit patterns aren't identical, they do exist in receive, right? So you can have a very strong signal arriving at an antenna that it can't hear because of the angle of, the angle of radiation, how the antenna interacts with the ground system and the things around it. So it's important to understand and measure and experiment with how we get the radiation to go where we want it to. So the second area I talked about is the ground. So ground is part of the antenna system. No matter what we do, the ground is either an active part of the antenna system or it's an influential part of the antenna system. Depending on the band, the height, all this stuff. If the ground is not reflecting, it's absorbing. And, I chose this graphic to show, the energy comes in here and it goes through, right? So if the ground itself is not part of the reflection plane, then it's sucking the energy, and that is not desirable in most cases. Colorado is a really good example of a place that sucks RF energy. Our soil is generally very poor in most of this state. So as far as the conductivity, so it is not a very good, the dirt in the rocks are not a very good conductor of energy to help be part of our ground system. Hence why we need radials. The last one is, all the other places that RF goes that we don't want it to go. Coax leaks. Coax leaks energy. You ever seen a loss chart for coax? That's because it leaks. If you put an X amount of energy in one end, and the same amount doesn't come out the other side because it leaks. It leaks through the braid holes. It capacitively couples. It comes out of the coax. Now, some coaxes are obvious. Feed lines are better than others, but and I shouldn't say coax because feed line can mean a lot of different things. RF. This is the other, RFI, right? Radio frequency interference. This is common mode current, energy coming back on the shield and going places where it wasn't. If the other half of the antenna isn't present, it will make itself present. If you feed an end-fed half-wave antenna and you don't have anything for a counterpoise, the other half of the antenna, it will find a way to make itself the other half of the antenna. It's usually the coax shield, but that could come back and be you if you're close enough. So it will find a way to make the other half of the antenna. All right, so let's move in a little bit onto antenna tuning. And as I mentioned earlier, tuning is changing the resonant point of the antenna, the resonant frequency of the antenna. The way we typically do that with our amateur antennas is by physical parameters. It's not the only way, but that's the way we typically consider tuning an antenna. So if we have an element on a beam, well, this could be a vertical too, it doesn't really matter. We adjust the length of each section, and the overall length is what determines what frequency that element resonates at natively. So here's a question for the room. We know that adjusting the length of the radiating and parasitic elements will adjust the frequency. What about, this is the boom, the elements along the boom. What does changing the spacing of the elements along the boom do?
Causes them to be at the right spacing to be a reflector or a corrector.
Yeah, it affects our gain and our pattern. It also affects the front, you know, in front to back ratio essentially, right? If we adjust the elements the right way, we move the power lobes the direction we want them to go, and we want to try to not hear behind us in say in a Yagi style antenna. So moving the spacing along there changes the lobes, the pattern, and the front to back, all the other aspects of the antenna. But it's the element's length that decides what native frequency it resonates at. Now, this is a very old antenna. It's still a very popular antenna. It's a tri-bander. It's on a 16-foot boom. So this does full band coverage on 10, 15, and 20 meters. But the max element's only 24 feet long. So how can that be, right? It's shorter than a full-length element would be at 20 meters. Physical adjustment isn't the only way we can tune an antenna. We can do it with capacitance and or inductance as well. That particular antenna, and it's hard to see on this picture, but we have the main element coming through here. There's some insulators, there's some straps, and we have parallel elements, and right here we have capacitors. And here's the schematic representation above with the mechanical below. By adding capacitance midway through the element, we electrically lengthen the resonant frequency of that while making it physically shorter, and it's still very efficient. So that adding capacitance and or inductance to an antenna system will change its resonant frequency. It will change its tuning. It has more effects than just moving the resonant frequency though, right? It also affects the bandwidth or the Q or quality of the antenna. In this particular case, this type of loading is called linear loading. It's instead of like an end load or top hat load, this is a linear loaded antenna element. So, question. Here's an antenna that has an inductor at the base. Here's an antenna that has an inductor in the middle of the antenna. Here's an antenna that has capacitive, or you might call it top hat loaded. And here's an antenna that's got a top inductor and a capacitor at the top of the antenna. What do you think's the most effective, most efficient radiator out of those antennas on there? It's kind of a trick question.
I'll say mid-element loading.
You're close, Dick. This is probably the most efficient one here. Okay, so, and I'm going to explain why, because you've probably heard this, right? You've probably heard that inductive loading is lossy. I think there's maybe some test questions on that. But all four of those designs make an electrically longer, physically shorter antenna. They're all less bandwidth than a native antenna that, that's the right length for its frequency. But there's a reason to use each of the different kinds. So let's talk about why capacitive loading is more efficient than inductive loading. If you go back to the theory, you remember in, I think, Tech or General class, in an AC circuit, a capacitive load leads the current, meaning it draws current at the peak of the voltage cycle, resulting in a higher power factor and less wasted energy compared to the inductive load, where current lags the voltage, causing a low power factor and energy loss due to the reactive power. This is where all the fake numbers come into play when you're looking at imaginary numbers into the reactivity. So resistance is only part of our equation, right? You have to consider reactivity as well. So capacitive loads don't have the lag that inductive loads do. Therefore, they make it more responsive to power changes. What does this mean in layman's terms? Inductors waste energy to heat far more than capacitors do. And because the inductors have to be to be most effective, they have to be in the current section. The capacitors can be in the voltage section. The antenna, if you're looking at, doesn't matter if this is a vertical, if this is a dipole, anything, the root of the antenna is going to be the current section. The ends of the antenna are the voltage sections. That's why antennas arc from the ends and not from the root of the antenna. The high voltage is out at the end, and the high current is nearer the root of the antenna. So hopefully that kind of gives you a base. When you're selecting an antenna, what's the easiest thing to do? Oh God, I could just put an inductor right at the base. It's convenient, it's easy to get to, and now I can do more bands. True, but it's not going to radiate as well as if you do something capacitive or even mid-load, right? Mid-load is still effective, and it's a balance between ease and effectiveness. Of course, it presents more physical challenges, right? It's harder to put a coil in the middle and keep the mechanical stability of an antenna, whether it's horizontal or vertical. But you'll find them there. If you look at something like the Cushcraft traps and stuff, they're midway out there. There's a lot of antennas that use that. VHF, UHF, right? Dual banders that you'll see a coil wound into the steel midway up and down there. Same principle. It's really important to remember that the ground, you can call it a ground, people call them, the terms are almost interchangeable, right? Counterpoise, image plane, ground, I mean, they really refer to the other half of the antenna. They're part of the antenna, and we have to put them into the equation. Now, here's one that a lot of folks don't know. When you're talking about HF antennas, it's true of anything, but it's more applicable for HF. What do we usually do with the radials on, say, a vertical antenna? We either staple them right on top of the grass, or maybe we dig a trench and put them 2 inches down. But elevated radials are way more efficient. Way, way, way more efficient. I can use between 2 and 4 elevated radials, 4 foot off the ground, right? And they're cut to length. The length matters. If they're 20 meters, I can use 4 radials that are cut for 20 meters, and the antenna is going to be probably 98% efficient. If I put 32 radials in the ground at the, doesn't matter what length they are, to an extent, that antenna is still going to be nowhere near as efficient as the 4 radiated or even 2 elevated radials. The trick is, though, they have to be cut to the right frequency, and that means the antenna only works on that frequency. So you can't effectively do that with a multi-band antenna unless you have stretched multi-band elevated radials out for each one of the bands. But it's interesting to know, you know, if you have just a 40-meter vertical out there and that's all you use, two radials out there is all you really need, and that antenna will scream compared to a monstrous array of things. Where does that come in handy? When you have your vertical on the back fence in your yard and you can't go in every 360-degree directions. You can only go 2 directions. There's an answer for you. With the caveat that it's band specific. All right, so moving on a little bit into tuning. Where do we measure? Where do we tune our antenna? Where should we make our measurements while tuning our antenna for resonance? We should always tune at the antenna, as close to the antenna as we can get. Now, if that's a VHF or a UHF antenna, we don't want to stand a foot away from it and tune it, because our capacitance that we introduce from our bodies will detune the antenna. But if that thing's up, you know, it doesn't really matter if that's a VHF or an HF beam or anything else. If it's on a tower, measure it at the base of the tower. Don't measure it in the shack. And why is that? Because here's the example. That antenna may be way out of tune, 4.3 to 1 SWR measured at the base of the antenna, but we have 300 foot of very lossy coax. Well, what does lossy coax mean? It means we lose power on the way out, but it also means we lose power on the way back. So all the power that's being reflected instead of radiated into the air by that poorly tuned antenna is being lost into the earth, into heat and things on the way back. So the antenna analyzer over here thinks the tuning looks great. 1.2 to 1, yeah, I'm good to go. You know, measure it in the shack, but the antenna 100 feet away, 300 feet away, it isn't radiating energy. I mean, some, but nowhere near what you want it to be. So always measure and tune your antennas as close to the antenna as you can get without you physically affecting the antenna. Now, this is so true. We've now put 600 feet of RG58 and shorted the end of the coax instead of an antenna. We still have a 1.2 to 1 SWR. We're losing, you know, 98% of the energy that we put out of there, both directions. So now it doesn't really matter what's at the end. That's how, you know, this is also a good indication of why poor coax, you know, good feed line is an appropriate choice. Now, quick side note on the feed line. We are so ingrained in using coax and we're so used to the loss factor in coax, but coax isn't the only thing out there. You know, if you want to feed your 40 or 80 meter vertical, if you feed it with open ladder line, you can put it 1,000 feet away and probably have a half a dB loss. So it really matters a lot. The feed line choices are, you know, managing an open feed line is a nightmare. You have to have all the right infrastructure and protect it from weather and everything else. But, you know, coax is, just remember, is not always the only choice that you have when it comes to feeding the antenna. All right, here's a trick. This is a high gain AV 640 or 680 antenna. This is a very popular antenna for people starting out in HF because it's, you know, 8 or 9 bands. It's a really effective antenna. It doesn't require radials at all because it's got a counterpoise system. You just stick a pole in the ground, stick this thing on there, and you're good from 6 to 40 or 6 to 80 meters. It does it all. And it's pretty effective. Usually multi-band antennas are such a compromise, they often don't work very well. And caveat, right, 40 meters and 80 meters are not wonderful on this antenna, but they do work. And these are very effective antennas. But how do you tune something like that? We've got to tune bands, you know, all these different bands, and we know that we can't tune them in the air because this antenna is, what, 27 feet high or something like that. So here's a trick. Put your antenna in the air. Use your antenna analyzer and find the center point of every band the antenna does and write it down. Now fold your antenna down, whether it's on sawhorses or something, you know, whatever. Measure it again. You will find that it's moved up. It's capacitively coupling to the earth, and every one of those resonant frequencies moved up by some amount. Now when you go in your manual and look, it says, oh, for 20 meters, 1 inch equals 100 kilohertz of tuning. Now take the difference between the horizontal and the vertical measurements and figure out, okay, when it was vertical, it was 200 kilohertz off. But when it's down, now it's reading, it's going to be somewhere else, right? I need to move it down 200 kilohertz. So I adjust until I get the new reading that's compared to I get the new ground reading compared to the last ground reading. Now when I put it up again, it's going to be spot on. We're very close to it. These antennas are, the first time I put one of these things up, I think I raised it and lowered it 50 times. I was so freaking tired from up and down until I thought about that. Yeah, see, 3 times, right? So you're not going to, but I'm not joking about that. It could be the difference between 40, 50, raises and lowers and 3 to do that. So that's just a quick little trick on tuning any antenna, multi-band or otherwise. It's really helpful to understand the difference between up and down, and you can use that to your advantage. It takes a little math, but. All right, so let's move into antenna matching now. Antenna impedance versus the feed system impedance, right? This is where we match the impedance of the transmitter receiver and the antenna system. Here's an example. This is a home-built antenna that I use 160 meters at home. It's an aluminum tubing antenna I built with DX Engineering slotted tubing, that you slide together. I can't remember. I think it's 82 feet high, which is really, really, really small for 160 meters. Very short antenna for 160 meters. It has T-load. It's capacitively loaded at the top. I have 2 33-foot wires, 14-gauge wires that come off the top that come to guide, insulators and guy lines that come down. I have tuned that antenna to 1.845 megahertz. So it is now resonant at 1.845 megahertz. But it's an electrically short antenna. This one has 128 radials under it, which is still not enough, for Colorado soil, but it's reasonable. But look at the antenna's resistive impedance is 12.5 ohms that represents about a 4-to-1 SWR. So I can't just feed that antenna. Even though it's resonant at 1.45, I can't just feed it with 50 ohm coax or it'll be a terrible SWR. So, and this is a slide from or picture from my last presentation. I built a 1-to-4 current unbalanced to unbalanced. That's my impedance matching transformer. 12.5 ohms on this side is 50 ohms on the coax side. They're both unbalanced because we're still dealing with unequal elements, the vertical and the ground plane, and the coax is an unbalanced system. So it's important to impedance match there at the antenna. Now my feed line all the way back is 50 ohm native. I'm not losing anything in the coax, which is what this is an example of. Poor pictures, I realize. Yes?
Go back to that last picture and tell us what each of those things are. You got that. What's the comment box there?
Oh, Comtech. Okay, so this is a 1-to-1. This is just a 1-to-1 current choke. All this does is remove, because you can never have a perfect. Oh, that's cool, Dave. You'll never get anything perfect. So there's going to be some common mode. You're going to have current on the shield of the coax a little bit. That's what that eliminates. So the coax from the shack is coming in here. It's a 1-to-1 current. Then it comes in here 1-to-4. So that's my impedance transformation. And this is just a tuning box. The antenna is natively resonant at 1.45 megahertz, but because it's short physically, it has a very narrow bandwidth. So I have relays that select an inductor to move the resonance up and down just a little bit. So as my radio tunes up and down, it automatically selects a coil tap or some silver mica capacitors. It selects coil taps below my resonant point and silver mica capacitors above my resonant point. So it just slides the resonant point of the antenna just a little bit up and down so that my bandwidth is acceptable wherever I'm operating. That's kind of a homegrown deal there. But
So how do you operate those relays?
so I did a whole presentation on this with my station automation. You can find it on the NCRC website. This is done with a microham station master automation system. It reads the cat data from the radio and sees where the band is, and it sends relay commands out to all the different things. There's a whole presentation on it if you want to see there. But, you know, so now we're matched, right? That's the important part. We've got an antenna now that's matched. So we put our radio, here's our trans-match tuner. Here's our coax, and then there's the antenna. 3-to-1 SWR out there at the antenna. Maybe we're using a long wire that's not resonant on any bands, right? That's a common thing, in-fed random wire, 40, use a 49-to-1 on, and it'll tune on any band. But you need a tuner. What's the problem with this setup here? I mean, it's convenient, but the problem is the coax is lossy, really, really lossy, right? So a lot of our energy isn't going to go out the antenna. It's going to go out the coax. And so this is convenient because your adjustment's in the shack, and it's cheaper because non-weatherproof smaller devices in the shack are easier. But it's not, you're not going to have a very efficient antenna system. You're not going to put a lot of energy out on the air. So, you know, putting the tuner, if you're using non-resonant antennas, putting the tuner at the antenna is the answer. Now, the price goes up exponentially for that kind of stuff because now you have to have control signals, weatherproofing, everything else. The guts of the tuner, you know, the transmatch are the same, but having it remoted 10x is the price. But if you want a really effective antenna, it's worth doing that, right? You can put a 43-foot vertical. That's another one of those common non-resonant antennas. 43 feet, all right, 43 is technically about resonant at 60 meters, but it's not resonant on any of our other bands. So that means its SWR won't be sky high across any of our bands. You put a tuner out at the antenna, and you have a very efficient antenna that's not resonant at any amateur band, but it's well matched all the way across. It's going to get a lot of energy out on the air. All right, so now we're going to do a little bit, some quick explanations, truths and myths, things like that to wrap this up. Does antenna height always improve efficiency or performance? No. Correct. Higher is not always better. Now, higher is better to a point. And usually what the general rule of thumb is your antenna is going to perform quite well once it's a half wave or more above ground. But you ever seen these big contest stations that have 200-foot high towers and they've got 4 sections of Yagis on them? Stack matches. Why do they do that? Because even though every one of those antennas is efficient and puts out radiation, every one of them, because of their height, puts out a different radiation angle. And so if you're working the Caribbean versus Russia or something like that, you're going to want to use either a different antenna or phase them together so that you can adjust basically radiation angle. So height is, once you're at above half wavelength, it's not always better depending on your goals. So what's the best SWR? This is something I hear people that have gotten past the Baofeng stage and are starting to do mobiles or bases at home, and people are tweaking. I got my SWR down to 1.1 to 1. That's great. If there's a dummy load out on the end of that, I can get my SWR down really, really well too. Doesn't mean it's a good antenna. There's not really a perfect answer to this, but generally we consider anything under 2 to 1 to be just fine. You're going to be pretty generally, even at legal limit, 2 to 1 is still pretty safe for everything. And there's a formula. If you're a math geek, you can plug all that in. If you're not, there's Google. But that shows you with 100 watts in, 2 to 1 SWR is about 11 watts back down the line, and that's pretty safe. You're not going to blow anything up in your radio from that. Yeah, your efficiency's plenty good enough there. What happens when it rains? We have our vertical out there. We got radials underneath it. We're in Colorado. What happens when it rains? Gets wet. Yeah, that's a good answer. Our ground becomes more conductive, and it can change things, right? Usually it's better. But it can change the resonant points of your antenna system depending on how your ground is laid out. If you have maybe just 4 radials out there, you'll change the ohmic loss in the system with more conductive ground, and it will change. The antenna will not have the same SWR as it does when the ground is dry. There are some major contest stations out there that water their antenna fields before a contest so that they can improve their ground planes underneath the antenna. Now, once you have an adequate radial field installed under your antenna, then you really shouldn't see much of a change at all when the ground is wet. If you've got an adequate image plane built out of wire under there, then it doesn't really matter that much. How do I know if I'm going to put up, say, an HF vertical? How do I know how many ground radials I need for my antenna to be effective? As many as you can get. That's generally a pretty good thing. But here in our soil, it's generally about 32. If you can get above 16, you start getting into a rather efficient antenna. At 32, the antenna is significantly sufficient, or significantly effective. If you really want to be a stickler about it, and you have the proper ground resistance measuring equipment, you can add radials until you stop changing your ground resistance by 2 ohms or less. If you add a radial and you drop your resistance less than 2 ohms, you're in that diminishing return phase, and you can add radials till you're blue in the face. It's not going to change much. But until you get to that 2 ohm point, and you can't measure this with a DVM, right? You can't put your digital voltmeter out there. You need something like, people call them Meggers. That was the company, but that's typical. There's a very specific instrument for measuring ground resistance. Yes.
So what do you think about ground mesh, welded wire fence?
It's fine if you can get enough of it. I'm sorry, the question was, what about mesh or wire fence type thing as your ground plane? It depends on, it works just fine, but usually the problem is you can't get far enough out from the antenna to be effective. You can, if you put 10 foot of ground under a 40-meter antenna mesh, it's going to be nowhere near as effective as if you put 4 radials that are 40 feet long.
Because the articles in the ARR antenna book say that a large number of short radials is better than a few long ones.
Yeah, so the comment was ARRL book shows that a large number of short radials is better than a few longer ones. So there's some science behind that one, and if you look into near field versus far field on the antenna, that's what it's all about. You basically have to cover the near field effectively with your ground plane to make it work, to make it efficient. If you can do that with a mesh fence or something like that, for sure, it absolutely will. But if you have, say a 40-meter vertical out there, you can put 100 6-foot radials under there, or 10 foot of chain link fence under there. Chain link's a bad idea, because it's not physically connected, or chicken wire. It's not going to be as effective as maybe 8 30-foot radials, because that 10 foot doesn't cover the near field radiation of the antenna, so you don't get you're still going to have a huge amount of ground loss beyond where your plane stops. Steve?
I recommend using welded link fencing if you're going to do it, because even the chain link, you get corrosion between the wires, and that'll give you all kinds of fits with harmonics and mod.
Yeah, that's true. And so, not making sure that whatever you use as a material underneath it has to be welded or mechanically sound. Now, if you put 10 foot of chain link, chicken wire or some horse wire under there, and then you add just a couple of radials beyond, that's going to be more effective than that's it. Cover a lot of the near field in there with the mesh, and then help supplement it with some of the radials. That'll help too. So.
What's the definition of near field in terms of wavelength?
It varies with frequency. What was the definition of near field when it comes to wavelength? So you.
How many wavelengths? Half a wavelength?
Off the top of my head, I can't remember. You'd have to look that up. It's in all the books, right? I'm sorry, I don't remember off the top of my head. But there's an easy way to calculate that. If you look at Google, even will do it. But all the antenna books, yeah. Sorry, I don't have a direct answer there. All right. So what about other tools, right? We've talked about our antenna analyzer a little bit. We can measure SWR. Field strength measurements. You want to know where your energy is radiating? A field strength meter can be very helpful. If you want to see, is my dipole, radiating, where I want. Now, there's a little bit of trick to that too, because we can't get too far into the sky. If you want to see some really, really cool experimentation that was done and research done, let's see, N6 TV. He was the owner of Force 12. He was the founder of Force 12 Antennas. He mounted a receiver on his drone and inject a very, very low signal in there and started flying the globe, right? Flying a sphere around the antenna and took signal strength measurements. And he was actually able to real life map out where all the lobes of the antenna were. N6BT. By the way, if you're into that stuff, and if you really want a phenomenal read, his book is called The Array of Light. It's Tom Schiller. It's an amazing book. It will enlighten you as to how all of this stuff comes together, and he's really good at talking in layman's terms about it all. So, return loss measurement. We talk about SWR. SWR is a ratio of forward going and return power. So it doesn't really tell us much about what's coming back. It just tells us relatively how much is coming back versus how much is going out. Return loss is the actual measurement of energy coming back to us that was reflected in there. So that can be very, very helpful because it's power dependent, right? I mean, we can look at return loss. SWR is it can be different when power changes, but return loss is always going to be the same. So if you have that number, it can be very useful. On-air testing, one of the most effective things ever for antenna testing and things like that. Whisper, if you've heard of that protocol, tons of things do whisper, right? You can do it from your computer with a sound card. You can do it with your phone tied to your transmitter. I have a couple of the little whisper. They're like little 2-inch cubes that run off of a single pen, a USB thing. When I was building a lot of my portable antennas for Summits on the Air, I would set up the same antenna, 2 antennas that I was testing in, 200 feet apart in the yard and put whisper transmitters on them. And that, it's something like 1 milliwatt of power output. Then you go back to the web an hour later and look, and you can see where in the world everything heard you. Great explanation of how well your antenna is radiating and where it's radiating. So whispers are really cheap, even though it takes a little time, right? You got to transmit and check. Yeah.
So I did some whisper stuff a few years ago. I did a few whisper things a few years ago and really got myself wrapped around the axle.
Yeah.
That if you want to test 2 antennas, you got to do it at the exactly
same time.
Timed.
Yep.
Because there's a whole bunch of other stations that could be on your same frequency, causing you to be lost in the mud.
Yeah.
And I did this, and 10 minutes later I did that. The answers are way different.
Yeah. And that's why, so, you can do whisper a million different ways. Soda Beams in the UK built a little tiny whisper transmitter. You can buy it at DX Engineering. I can't remember how much they are. They're not very much. They're powered by a USB, micro USB. I just use those little single cell phone charger pack things, like you find at conferences that they give them away, and I power my transmitter. There's literally an SMA connector on one side, a push button on the top, and a 5-volt USB on the other side. That's the only thing on the little box. It's about 2 inches square, 1/2 inch thick. And you configure it with your phone through USB of what frequency, power, and all that. Then I have 2 of them, and I put them on the antennas. All you have to do is watch a time source, and when it hits 0, the minute it hits 0, you just press the button. And then a minute later, go press the other one, and now they're synced together. Now you can go take the 2 data sources that you have together and go look them up on the web. They're super, super cool.
So if your yard is big enough to have 2 antennas.
Or go to a park. If you don't need to see the data in real time. It gets recorded and it's there. So if you don't have enough room in your yard, go to a park and do it. Put it up there for an hour, have a picnic, tear it down, go home and see your data. So, all right. Now, wrapping it up. A couple of points. We want to make sure we tune our antenna at the antenna. We want to make sure that we have paid attention to our ground, our image plane, our counterpoise. We want to use high quality and appropriate feed line and connectors. Make sure the signal is getting it out there, understanding the difference between all that. Here's one, this goes along with learning how to use your radio. Learn how to use your test equipment, even if it's simple, right? Even if it's nothing more than a MFJ antenna analyzer or a field strength meter. Learn how to use it properly, and it will really pay dividends in there. If the little VNAs are very popular nowadays. Learn how to calibrate them and read them properly. Very useful. If I had to wrap the whole presentation up in a key takeaway, here it is. The efficiency is not just tuning for low SWR. You've got to consider feed line, impedance matching, the environmental factors, and the grounding for maximum radiated power. Joe.
Have you tried for portable operation the magic carpet and or Faraday cloth?
I have not. I'm not actually familiar with those products. Mm-mm.
Yeah, it's been out for, I would think, a year or so. A couple people from England have actually tried it. It's supposedly supposed to be really great and fairly cheap. You can get it on Amazon. So.
Yeah, worth looking. Yeah.
Has anybody else tried it? I guess I'm all alone. I've never tried it. I thought about getting it.
Yeah. Would love to hear. Yeah. So that's all I had for you today, other than any questions, and I appreciate it. Dick?
That was a super presentation. I've got about 17 questions here I'd like to ask. Rapid fire.
Okay.
Number one, quick one. On the coax loss, I think what you're trying to say is the radiation loss through leakage is going to be much more than the ohmic loss due to heating, just the resistance, of the copper going out and back.
Yeah.
Okay.
Yeah.
All right. And secondly, on the vertical, just a comment, I use a telescoping 17-foot vertical, go out to Boyd Lake and play with it through POTA. And I did a test where I just put like 2 radios, and they're like about 11, 12 feet long, okay? And they just threw them on the ground, okay? And then I did 4, then I did 6, then I did 8, and I got an antennalyzer, and I charted the plus. And you can really see the difference. So I'm going to have to go back now and do the test all again and do it with return loss. But something that you also said, because a vertical is basically half a dipole, so if it's, quote, well matched, it'll be down around 36 ohms.
Yeah, that's correct.
So we're still going to have a mismatch between the coax. I don't know if it's worth to make it a 1.5 to 1 unon.
Yeah, you can.
Yeah, because I know she used a 4 to 1 on yours, and
well, I used a 1 to 4.
1 to 4. Sorry.
On that particular one, because it was 12 and a half ohms on that one.
Right.
If you want to learn about unons and balons and making it almost any ratio you could ever imagine and how to design it, Jerry Cizek wrote a book called Balons and Unons, and it's a phenomenal book on all of that design work. Shows you how to build and understand the math behind really efficient impedance transformers.
Yeah, I've probably OD'd on YouTube videos for Anand's
Yeah.
for in-fed half waves, which is what I'm
That book is
I'm
my
playing with.
Bible for making impedance transformers.
Yeah. Okay, where's the third one?
Court
Well, I'll tell you what, I'll pass it because I can't find it right offhand. But yeah, got a lot of good data here. Thanks.
Yeah, well, you know, the slides will be available. I think everybody knows how to contact me. Worst case, my call sign at ARRLnet or techchair at ncarc.co. You know, feel free to reach out, and you know, hopefully this was helpful to, at least some tidbit in there was helpful to everybody. This stuff I find fascinating, so thank you.
This presentation was brought to you by the Northern Colorado Amateur Radio Club. For more information, visit our website, ncarc.net. Thanks for watching, and don't forget to like and subscribe.